Hi everyone, my name is Claire Tomlin. I'm a professor of electrical engineering and computer sciences at Berkeley. And this is the 15th module in a series of modules that we're recording to support the course Linear System Theory, EECS 221A at Berkeley. The topic of this module is Dynamical Systems. And it's a transitional module that takes us from the previous work that we've been doing, which has been linear algebra, several modules on linear algebra, some modules on existence and uniqueness of solutions to differential equations. And now we transition over to linear system theory, when we're actually going to be using this material to understand and develop a theory of linear systems. So we're going to start generally with a definition of what it means to be a dynamical system. So it's a term that we use a lot, a dynamical system. What does it mean? What does it formally mean? And so we try to nail down the pieces that we need to be in a dynamical system using the following definition. So it's got a number of different elements in it. And then we have some axioms that these elements of the dynamical system have to satisfy. Okay, so a dynamical system D, say, has a bunch of elements. It's got 5 things in it. It's got an input space, a state space, an output space, a state transition function, and a readout map. So these are 5 different things. These are sets of elements, and these are functions. And so let's say a few words about what these individual things are, and then we'll talk about how they fit together. Perhaps we'll do a couple of examples to show how they fit together. Okay, so U are inputs, so they're input functions. And so we say that U takes typically a function of time and maps it over to a set which we'll call capital U. And this is a set in which the inputs lie. Typically, in our systems, capital U is Rm or Rn. Let's actually be precise. Let's call it Rni. So that little ni represents the dimension of the input space. So in this notation, these represent the functions, and this capital U, which is typically Rni, represents the space in which those functions, the range of those functions. And so Y, let's skip over to Y. These are output functions. The same thing. So Y is a function of time. So it takes R plus over to some set Y, and we'll set that to be Rn out, where n out represents the dimension of the output space. Sigma is the state space. Okay, so we have a function x of time, which takes us to sigma. And typically, in our case, sigma is equal to Rn. Okay, so in the differential equations that we've been studying in previous modules, x represents, or it will represent, a candidate solution or a solution to the differential equation. So x instantiated at a point in time is a vector in Rn. Okay, so those are the 3 spaces, and then these functions S and R are called the state transition function and the readout map of the dynamical system. So S is the state transition function. So S takes, well, it's a function of 4 different things. It maps time, initial state, and input to a state. Okay, so it takes copies of time. Actually, that's something we didn't talk about here. So we have a dynamical system, and all of these functions, we've called them functions of time, or R plus. We don't actually need to define time to be R plus. We could have a a discrete event dynamical system or a discrete state dynamical system where time is actually not a continuum. It's not defined on the real line. Rather, it's defined on the set of integers. So we could define, let's be a little more general. Let's define capital tau to be time. And tau can either be equal to r plus, or r, if we want to include negative time, or tau could be the set of points n, t, so integer n, t, so n here is an integer. So this means the set of points n times t, where capital T here represents some kind of sampling time. Okay, so that allows us to think about continuous time systems as well as discrete time systems. And then we can generally redefine the time here. We don't have to change anything except for the time axis. So let's make this tau instead of r plus, tau, tau. And then the state transition function will map a copy of time, the state space, and the input function space over to the state space in the following way. So the meaning of this then is that S takes the current time, the time at which we started, which we'll call t0, the value of the state at which we started, which we'll call x0, and some function u, which is valid between these two times. So starting at t0 and going to time t, t0 to t. And it gives us the state at this particular time t. So it's called the state transition function because it transitions the state from its value at time t0 to its value at time t, where over that time interval, the input function u was used as an input or some kind of guide to the system. Okay, so that we've got these specific entries into the function to mean specific things. The time now, the time at which we started, the value of the state at which we started, and the input function between t0 and t. And so that function has some dynamics. It's got some memory associated to it because it's transferring from the state at some initial time to the state now using the input over that time interval. So that's the state transition function. And then the last element is called R for readout map. Readout, sometimes it's called the output map. And the readout map, R, is a function of time. Okay, so again, we can write it this way. It takes tau, let's just write it this way. It takes the current time. It takes the state at the current time. And it takes the input at the current time. And it gives you the output. So it gives you the value of y at the current time. So if we wrote it out more generally like this, R would be a function of three elements, tau cross the state space sigma cross the input set. So it's not the set of input functions, it's this set here. It's the value of u at the current time. And it gives you the output at the current time. Okay, so unlike the state transition function, which has this notion of memory, dynamics, it's got it within that definition or within that notation, there's some notion of having started at an earlier time and evolved up to the current time. The output map is just static. It just looks at what the current time is, what the state is right now, what the input is right now, and it gives you what the output is. So it's a static map where this is a dynamic map. Okay, so we've got a definition of a dynamical system. We've just defined it in terms of its entities. Input, states, outputs, state transition function, readout map. All right, let's do an example. Let's do some very standard examples. So one thing might be a circuit. This is a dynamical system. Let's write down the circuit example. And this is a simple electric circuit. It's got a capacitor and 2 inductors. And it's got some voltage source here. Let's let the voltage source be the input. So it's a scalar input function over time. Here's a resistor. Here's an inductor. Here's a capacitor. And here's another inductor and another resistor. Okay, the storage elements in this system are the capacitor and the 2 inductors. So let's see, let's give everything names. Well, this will be R1, R2, L1, L2, and C. And let's call the voltage V1 across that resistor. And the voltage across this resistor we'll call the output. That's the thing we're going to measure. That's what we're interested in. So that's a voltage. I could call it V2, but I'll just call it Y here. Just like I could have called that an input voltage, but I'll call it U to be an input. And then we'll define the fluxes with respect to the inductors L1 and L2. Okay, so in terms of, so we'll say flux Phi1 for inductor 1 and Phi2 for inductor 2. So the voltage across inductor 1 is Phi1 dot, and the voltage across inductor 2, and I'll use that sign notation, is Phi2 dot. And Q will be the charge in the capacitor charge. So then Q dot represents the current through the capacitor, Q dot. Okay, so this current is just Phi1 over L1 and Phi2 over L2. Okay, so that's getting a little small there, but I hope you can see it. So current Phi1 over L1, current Phi2 over L2. Okay, so given that description of the circuit, we can use laws of physics, in this case the KCL and KVL. Kirchhoff's current law, which says that at any node, the sum of the amount of current going in must be equal to the amount of current coming out. And Kirchhoff's voltage law, which says that if you look at any closed loop in a circuit, the sum of the voltages around that closed loop has to be equal to 0. And we can use those laws to derive what we call the dynamics of this system, or the dynamic equations. Okay, so if we do that, then we can quickly arrive at the following. So Q dot is equal to minus 1 over L Phi1 minus 1 over L1 Phi1 minus 1 over L2 Phi2. Phi1 dot, so there you see in that first equation an application of KCL. 1 over CQ minus R1 over L1 Phi1 minus U. So that's applying KVL around this first loop, and then applying KVL around the second loop, we get Phi2 dot is equal to 1 over CQ minus R2 over L2 Phi2. Okay, so now we look at that equation and we make sort of or those sets of equations, and we make some remarks about it. The first remark is that on the left-hand side, we have first derivatives of elements in the of values of interest in the circuit. And on the right-hand side, everything on the right-hand side is a function only of these variables, the variables before we took their first derivatives, and of the inputs. So if we defined for this example the state to be Q, Phi1, and Phi2. Okay, so that's my definition of what my state X is, or X1, X2, X3. Then I can rewrite that set of 3 first-order differential equations as a vector-valued differential equation, which looks like that, where on the left-hand side, I have a first derivative of this vector x. So that's the vector x1 dot, x2 dot, or x3 dot, or q1 dot, phi1 dot, phi2 dot. And on the right-hand side, I have a vector-valued function where the elements of the vector are just minus 1 over L1 x2 minus 1 over L2 x3. So this is x2, x3, x1, x2, x1, x3, and u. Okay, so it fits into this form here. Y, the output in this case, is just equal to the voltage across that resistor, which is simply R2 over L2 times phi2. Okay, so it's just a simple function of the state. It's just a function of x3 and this constant here. And the input is this input voltage, so it's a function of time. Okay, so here we have a differential equation. We have an output, we have an input. What do we have in terms of a state transition function? So we can think about this immediately as the readout map. It doesn't depend explicitly on time, but it does depend on the state at the current time through x3. It just depends on the third component of the state at the current time. Okay, so it's an algebraic equation in the state. The state transition function is a little more complicated because we remember the state transition function has memory associated to it. The state transition function says that if you have your current time, the time at which you started, the value of the state at which you started, and the input function over that time horizon, then you should be able to use the state transition function to get the state at the current time. Well, we don't have that here. What we have is a differential equation describing how the state changes. And we could assume that we're given some initial state. So we're given some initial value of fluxes and charge. So thinking back to what we've just done in previous modules, if we solve this differential equation, what that solution will give us. So let's just go down here and think about if we solve that differential equation and came up with a solution x of t by coming up, suppose we had a known input voltage profile over time. We plugged that into our differential equation, and that gave us some particular value of u of t, which was known. Then we could really just absorb u of t into f and rewrite this equation as x dot is equal to f bar of x with some initial condition. Then we could solve that differential equation, or if we could solve that differential equation, and it would give us, based on that initial condition and that input, it would give us what the state is at the current time. So solving this differential equation gives us access to what that state transition function is. The state transition function tells us how the state transitions. In order to get that information, we need to solve that differential equation. But if we could, and we know under what conditions of f there exists a unique solution, then we can get that state transition function. Okay, so that's sort of a candidate example of a dynamical system. And then let's conclude today just by looking at two axioms that any dynamical system must satisfy. So we've defined a dynamical system so far in terms of these 5 elements. We did an example, but there's 2 things that any dynamical system must satisfy, and those are called the axioms. The first axiom is called the state transition axiom. State transition axiom. And the second axiom is called the semigroup axiom. The state transition axiom says the following thing. It says that if the inputs are the same over a time interval and you start at the same initial state, then the state transition function will give you the same result at the end of that time interval. So if you have 2 inputs, u and u bar, but u is equal to u bar, or let's call it u tilde. U is equal to u tilde over some time interval t0 to t1. Even if those inputs are wildly different from each other before t1, before t0 and after t1, then the state transition function starting or ending at time t1, starting at time t0 with initial state x0 using u will be the same as the state transition function at time t1, starting at time t0 with initial state x0 using input u tilde. So you only need the inputs to be equal to each other over the time interval of interest in order to get the states to be equal to each other over that time interval. So this would hold for any t within that interval t0 to t1 over which the inputs were equal to each other. Okay, so that says, this axiom says something a little bit deeper. It says that what happened before t0 and what happens after t1 is not of importance when you're looking at the state in that time interval. Somehow, all of the information of what happened before t0 is encapsulated in x0. And all you need to determine the value of the state at any time within that time interval is the value of the state at which you started and the input over that time interval. So if the inputs are the same over that time interval, then the state values are going to be the same over that time interval. Remember, s at t1 or s at t gives you the value of the state at that time at t1 or at t. The semigroup axiom says the following. It says that, let's pictorially think about it. Suppose you started the system, let's let this be our axis in t, and this is time t0 and time t1. And let's think of some intermediate time here, t star. So t star is inside that time interval. Suppose you started this, and let's let this axis be x. So suppose you started at the system at state x0 at time t0. And you applied some input u of t over that whole time interval. Here's my u of t. So start the system at time t0 with state x0 and apply this input over the whole time interval, and then look at the state at time t1. That is equal to, the value of the state at time t1 is the same as if you started at time t0 at state x0, you evolve the state to time t star using that portion of the input between t0 and t star. You stopped, you got some value of the state x star, and then you started again, and you started at time t star with state x star, and then you continued evolving the system to time t1 using that remaining portion of the same input. Then the values of the state at time t1, given that first way of just going the whole row without stopping, versus stopping, recording, starting again, and going, you get the same value of the state at time t1 regardless of how you do that. And so we state that semigroup axiom as follows, that the state at time t1, given that you started at time t0 at state x0 using input u, and now we recognize, because we know the properties of a state transition function, that this is the input function defined over this time interval. Okay, so we don't have to keep saying u between t0 and t1 because it's defined by those points in time. That is equal to s at time t1, given that we started at time t star with an initial condition, which is actually s at time t star, given that we started at time t0 at state x0 using input u between t0 and t star, and then using input u between t star and t1. Okay, so that's called the semi-group axiom, that if you break up time into those intervals, and evolve, as long as you're always using pieces of the input that are derived from the same input function, then the result is going to be the same. Okay, so in summary, we have a dynamical system defined in terms of 5 objects: an input space, a state space, an output space, a state transition function, and a readout map. We can think about the state transition function in terms of what we've done as differential equations as, being the solution or some representation of the solution of that differential equation, where the initial state, the initial time, and the input have been made specific. They've been given to you. And then we have 2 axioms associated to the dynamical system definition: the state transition axiom and the semi-group axiom. So as long as if somebody gives you a candidate dynamical system and says, is this a dynamical system? As long as you can identify those 5 components and you can show that these 2 axioms are satisfied, then you can say, yes, this is a dynamical system. Okay, so in the next module and in the ensuing modules, we're going to focus on particular kinds of dynamical systems. Linear dynamical systems is really what we'll be focusing on for the rest of the course, but we'll also talk about what it means to be a time-invariant dynamical system. And we're going to talk both about time-invariant and time-varying linear dynamical systems for the rest of the course. Thanks.